The objective of this video is to identify symmetry conditions for fractional slot windings, and second, to summarize the parameters of base windings. So we're going to be talking about how to determine if a certain combination of slots, poles, and phases can produce a symmetric winding. But before we go there, we should probably talk about what a symmetric winding is, or what it means for a winding to be symmetric. And I've put on the screen two definitions for whether or not you have a symmetric winding. The first is that a symmetric winding will create a rotating field when it's excited by symmetric currents. What are symmetric currents? Well, in a three-phase system, symmetric currents are sinusoidal currents that have the same magnitude and are delayed from each other by 2 pi by 3 radians. So these are the three-phase currents that we've been writing out when we derived our rotating current density and electric loading expressions. So that is to say that when excited by symmetric currents, a symmetric winding will produce a rotating field in the air gap of the machine. The second definition is in terms of the electric behavior. So the first definition was in terms of the magnetic behavior, the second definition is in terms of the electric behavior, and the second definition states that when a winding is symmetric if it has an equal magnitude back EMF in all phases, which is separated by alpha pH radians. So that is that each of the phase windings should have the same magnitude of back EMF, but the back EMF should be delayed from each other by the phase spacing in our phase system. In a previous video, we talked about different phase systems, and for a three-phase system, you had a phase spacing of 2 pi by 3 radians. So you'd expect phase U, V, and W voltages to be the same magnitude, but separated from each other by 2 pi by 3 radians in time. And as I remarked earlier, only certain combinations of poles, slots, and phases will allow you to install a winding in the stator that satisfies these symmetry conditions. And we're discussing this now because it's an issue that arises in fractional slot windings. It turns out for integral slot windings, that is where your slots per pole per phase is equal to an integer number, you automatically satisfy the symmetry conditions. But for fractional slot windings, you have to perform additional tests to determine if your value of P, Q, and M, that is your value of pole pairs, slots, and phases, can be used to produce a symmetric winding. And so the first part of this video is deriving, or rather summarizing, those symmetry conditions so that you can use it as the first step in any design process. Before you bother laying out your winding, you'll test whether the winding can satisfy the symmetry conditions. And these symmetry conditions can be summarized as two requirements. The first condition is that you must have an integer number of coils within a phase. And we've talked previously about how to calculate the number of coils that you can have within a phase, depending on whether this is a single layer winding or a double layer winding. And I'm going to summarize this now, but basically you look at how many slots you have and you divide it by either M for a double layer winding to calculate the number of coils, or 2M for a single layer winding. And so this is the first condition of symmetry. We're going to adjust this, or we're going to work on this expression a little bit to distill it down to some simpler forms that we can quickly use to identify whether our winding is symmetric or not. But before we do that, I need you to recall the following. Recall our definition of little q as the slots per pole per phase. This little q is a very important parameter that's going to come up time and again when we talk about fractional slot windings. And so, well, by definition, little q is slots per pole per phase, which means it's going to be big Q divided by 2 times P times M. And we said that we're going to be writing this in terms of a fraction of Z by N, where this fraction is fully reduced. That is, Z and N are integers that contain no common divisors. And if we rewrite this, we can solve it in terms of Q, or big Q, so we can calculate our number of slots as being 2 times our number of pole pairs times our number of phases, and it would be times Q, which is equal to Z by N. And so what we're going to do is we're going to plug this into these expressions and simplify. And for a single layer winding, we get that Q by 2m, which is the number of coils per phase, is equal to little p times our slots per pole per phase, which is then equal to p times z by n. And this quantity, p times z by n, must be an integer in order to have an integer number of coils. And since z by n is a fraction and it contains no common divisors, this means that p by n must be an integer. And this, what I just wrote out here, is math notation for saying that p by n must be within the set of natural numbers or integers. So this is already a quite useful expression. When motor designers talk about using fractional slot windings, they oftentimes focus on the value of n. So not only do we think about Q, but we immediately resolve it into z by n, and then we focus on this value of n because it tells us a lot of information about how our winding will perform, which we'll be talking about a bit more later. So it's natural to talk about our symmetry condition in terms of our number of pole pairs and the denominator of our slots per pole per phase. So we'll do the same thing for the double layer winding. And in the case of the double layer winding, 2 times p divided by n must be a natural number, must be an integer. And you can see that this gives us a lot more flexibility. So for example, in a single layer winding, we could not have p be an odd number if n was equal to 2, because it simply wouldn't work, right? But in a double layer winding, this 2 will cancel with n being 2, and p can be any value in that case. So that was our first requirement for symmetry, was that we need to have an integer number of coils per phase. Our second requirement is that we need our phase angle to be an integer multiple of our phasor spacing in our star of slots. So we previously talked about how to calculate our phase angle of a multi-phase system, and we've talked about this value in our star of slots, alpha z, which is the spacing between adjacent phasors. It is not the spacing, it's not the phasor spacing between adjacent slots, it's rather the spacing between adjacent phasors within the star of slots, because remember, in fractional slot windings, adjacent slots do not necessarily have adjacent phasors within the star of slots. We talked about that in a previous video. And so if you will recall from our previous videos, we have given the calculation for the phasor spacing, or the phase spacing between phases in a multi-phase system, depending on whether the system was a normal system, that is, it has an odd number of phases, or it was a reduced system, that is, it has an even number of phases. And we also talked about how to calculate the angle between adjacent phasors in our star of slots as being 2 pi divided by q prime, where q prime was equal to our number of slots divided by this value t, where t was the greatest common divisor of q and p. That is, the greatest common divisor of our number of slots and our number of pole pairs. And so now we can plug these expressions into each other to figure out this symmetry condition. And we're going to do this by dividing alpha phase by alpha z. That is, our phase angle spacing divided by our phasor spacing, and impose a constraint that it must be an integer. And so you'll see here I've plugged in alpha pH right there for a normal system, and on the right I've plugged in 1 over alpha z. So if I cancel terms, I get this simple requirement: q prime divided by m must be an integer. And then I can do the same thing for a reduced system, where now I'll be using this expression for alpha phase. And so we get this condition that for the reduced system, our q prime by 2m must be an integer. And we can show, if we work on these systems, I'm not going to show in this video, but you can show that this is equivalent to requiring that n and m be co-prime with each other. That is, that n and m can contain no common divisors other than 1. And we can write this as a math equation by saying that n must be perpendicular to m. So these are our two symmetry conditions. The two symmetry conditions were, again, that we required to have an integer number of coils per phase, and we could express this in terms of p and n, and that we need our phase angle spacing to be an integer multiple of the spacing in our star of slots. And we were able to express this in terms of requiring that n be coprime with our number of phases. So we'll now summarize our symmetry conditions in a compact form for you to archive. You'll be referring to these frequently, so please make sure you understand how to use them. So in summary, we have these symmetry conditions based on our number of pole pairs and the denominator of our number of slots per pole per phase, that is n, and our number of phases. So this effectively imposes constraints on our number of slots, our number of poles, and our number of phases. And I want to note that for integer slot windings, we automatically satisfy these. So for an integer slot winding, q is an integer, little q is an integer, which means that our denominator of it is always 1. So that means that n is 1, and you can see that if n is 1, all of these conditions are automatically satisfied. So that was the first part of our video, which was identifying symmetry conditions for fractional slot windings. The second part of our video is going back to talk about base windings and summarizing some important parameters of base windings. So the definition of a base winding is it's the shortest independent section of a winding that satisfies the symmetry conditions. And we talked about base windings a little bit previously in a different video, and here we're going to formalize it by first categorizing fractional slot windings into two categories, and then doing a calculation for the base winding length based on this. And so, as I said, there's two categories. The first category is called a first grade winding, and a first grade winding is a winding where q prime divided by m is an even number. And if you do a little work on this, you can prove to yourself that n, the denominator of our slots per pole per phase, is always going to be an odd number in this case. And so, if n is going to be an odd number, that means that this pertains to integer slot windings as well. And so we can see that if q prime by m is an even number, it is always going to satisfy these conditions for our first symmetry requirement. So if q prime by m is an integer, it automatically satisfies this requirement, so we're good. And the fact that it's an even number means that we can always divide it by 2 and it will still be an integer. So from this we can say that we are always able to have a base winding length which is equal to q prime. It doesn't matter whether we're talking about a single layer winding or a double layer winding. However, that will not be true in our second case. So in a second grade winding, q prime by m is an odd value, and you can work on this to show that that means that little n, the denominator of our slots per pole per phase, is an even number. And so if this expression is an odd number, and we go back to our first condition of symmetry, we can see that a single layer winding will not satisfy the symmetry condition because we've got this pesky 2 in the denominator, while a double layer winding will always satisfy the symmetry condition. So now we can comment that if this is the case, our base winding needs to be 2 times q prime for a single layer winding, and it can just be q prime for a double layer winding. So this gives us insight when we go to lay out our winding. If we know it's going to be a first or a second grade winding, we can immediately say things about what the shortest independent winding length can be. And this matters because we may want to be connecting our base windings in parallel or in series. And so if you have an odd number of base windings, then you simply can't connect it in parallel. And there are many more parameters that are useful in the design process which can be derived for these two winding types. And for this, I want to refer you to a table in our book. And that table is table 2.7 in section 2.11 in our textbook. So please review this table and review the results for the different types of base windings, the first and second grade base windings. So in summary, this video has identified symmetry conditions that can be used to determine whether a fractional slot winding is symmetric, and it summarized parameters of base windings. Both of these analysis techniques are necessary in the design of fractional slot windings. Your very first step in designing a fractional slot winding is going to be to test the number of slots, poles, and phases against the symmetry conditions that are summarized in this box. And categorizing your base winding as a first or a second grade winding is useful in terms of designing it and studying how it's going to behave.